Alrighty, everybody. Okay, not really sure what that's was about, but it looks like we are streaming live. So welcome everybody to the Grand Strand Astronomers October 2023 meeting. So I hope everybody's doing pretty well. We're all before we get started, we've got a couple of announcements and comment I'll make. One is that I hope everybody enjoyed getting out in September. We had our dark sky observing session, the first time in probably 5 months, 6 months that we were able to get out under dark skies. The conditions were very, very nice. Seeing was very, very steady, and we got some good viewing in. We had about 20 people come out to Hampton State Park. So had a really good night, and hopefully that this is going to be only one of many this fall. So hopefully we'll have good luck here in October as well. Although that would be October 14th for the session, which is a week from Saturday. Right now the weather conditions are not looking ideal, but so hopefully it will clear up, right? Hopefully that front will move a little faster, and we'll actually get the backside of that front and have clear weather. I also want to mention two upcoming things that for public observings. One on October 14th is for the partial eclipse. As everybody knows, there's an annular solar eclipse over a fair amount of the U.S. On Saturday, October 15th. Of course, it's not going to be an annular eclipse here. It'll be a partial eclipse with the sun about 40% covered. So we're going to try to do an event in conjunction with Coastal Carolina University. We got a park there. Police are going to rope off part of a parking lot where we can set up. The university has multiple 3 H-alpha solar scopes. And I know I've got an H-alpha solar scope, so we'll need some help. Even if you don't have a scope, it'd be great if you could come and help out. And, we could just show some people the sun, because the partial eclipses look pretty good through a H-alpha telescope. So we're going to try to do that. Unfortunately, the weather conditions are not looking ideal right now in the long-term forecast, but that could change. So hopefully we can get some help on that day. And that night, of course, the dark sky observing falls on the same day because, of course, it's new moon, which is why we have an eclipse. We'll see how all that shakes out. The other thing is on Friday, October 20th, I think the website may say October 21st, but actually it's October 20th. We are going to try to do a public observing at Huntington Beach State Park. So they're going to let us set up. We'll park in the parking lot. We can set up on the grass right by the parking lot, and they're going to advertise it, and that's going to run till about 10 o'clock at night when they get ready to shut down the gates. So hopefully we'll get some folks to come out for that as well. So those are two things that we're looking forward to.
So what date was that for the last one?
October 20th.
Okay, thanks.
Friday, October 20th. So hopefully we'll get good weather for both of them. That would be awfully nice. Yeah. So I guess what I was going to try to talk about today, I was going to try to talk a little bit about the sun, so that anybody coming to help can watch this video and will know a little bit about the sun, right? Although maybe all of you know all kinds of stuff about the sun already. So does anybody have any questions before we get started? No. Okay. If you'll pardon me for 1 second here while I sorry, having some technical issues here. How's that? Did everybody see that? Okay, thank you for the thumbs up. Yeah, we'll talk a little bit about the sun for those of you that may be familiar with it, may not be too familiar with it, but who knows? I'm talking to a group of experts here, but maybe some folks watching, right? Let's see. Oops. Okay. Well, this is my old one. Sorry about that. When you look at the sun, it's kind of interesting. It's much different than everything else in the solar system. And for example, if you look at the size of it, it's huge, right? The radius is about 700,000 kilometers. So you can fit about 110 Earths across the face of the sun, right? It's much bigger than much bigger than anything else in the solar system. It kind of really dominates the solar system. This is really true when you talk about the entire mass of the solar system, which we can figure out using Kepler's third law. And so basically, it's over 300,000 times the mass of Earth. In fact, when you add up all the mass in the solar system, the sun makes up about 99.86% of it, right? So well over 99% of the solar system, the mass is all in the sun, right? So that's why it's kind of the gravitational center of it, because it's really all the mass. Even when you think about things like Jupiter being very big, but compared to the sun, it's really nothing. The rotation period. So of course we can observe sunspots, right? And when we observe sunspots, it tells us basically a little bit about the rotation period of the sun and the fact that it does rotate. Notice it rotates about every 25 days on the equator. And by the time you get to the pole, about every 36 days. Of course, it has this differential rotation because it does not have a solid surface, right? If it had a solid surface, the rotation time would be the same, but because it doesn't, that means different parts of it can rotate at different speeds. And you can also see, it's kind of interesting, the interior rotation speed is actually faster than the speeds at either 60, by the time you get to 60 degrees latitude, or at the poles. So the interior is actually rotating much faster. So again, because it's just a ball of plasma, that's why you can get all this differential rotation. Of course, we can look at the spectra coming off of it. And, fortunately for us, or, basically because of it, our sun peaks right around in the green. So basically you get kind of almost an even amount of all the different colors, which is why it kind of looks white to us. That's, and looking at where our sun peaks, looking at the black body curve, you can find out the surface temperature is right around almost 5,800 degrees Kelvin, or sorry, 5,800 Kelvin, 5780 to be exact. And I always find it interesting with the luminosity, and this is how much energy the sun puts off, right? So it's 3.86 times 10 to the 26, which is a huge number, right? It's like taking 3.86, it's like taking 386 and adding 24 zeros after it. I have kind of trouble myself. I have trouble with big numbers sometimes, really appreciating how big they are. So I tried to come up with some comparisons. And that would be like 1 million, billion, billion, 100-watt light bulbs. So that'd be a lot of light bulbs. How about this? 1 trillion, 1 megaton nuclear bombs. We tend to think that a 1 megaton nuclear bomb is pretty powerful, and it is, but the sun basically is 1 trillion of those. And then, oops, sorry. And here's another one. It's 2.3 billion times the worldwide energy use in a year. So I tracked down the worldwide energy use. I think I couldn't find figures for last year, but I did the year before. And basically, it's about 2.3 billion times that. So it's actually a lot of energy that comes off the sun. Of course, this is so I did a little picture with the approximate size of Earth compared to the sun. It's much, much bigger. Whenever you see these prominences coming off, like you see here, then you see they're actually huge. Let me actually pull up a pen here. And you see these prominences right here. You actually see that, they're actually much, much bigger than Earth. They look small in the sun sometimes, but they're actually really huge. So how did we, it was really kind of interesting up till really the early part, almost 100 years ago, or basically 100 years ago. They didn't know what the sun was made out of, right? The leading theory, it's kind of interesting actually. The leading theory was that it was just like Earth. It's made of the exact same stuff of Earth, except it was heated up really hot. And that if you heated Earth really hot to a high temperature, it would look exactly like the sun. And that really was the widely accepted scientific theory. So you introduce Cecilia Payne Kapushkin, and I know I pronounce everything with a Russian accent. I'm sorry. So I forgive anybody from Eastern Europe who knows how to pronounce that correctly. And she's not very well known as an astronomer, but she was born around 1900 in England. And she basically was studying something else. I'm trying to remember some other field completely unrelated to astronomy, and then went to see a lecture by Arthur Eddington. So basically, I'm sorry, I left a note there more on him and orbits and gravity because I use this in my class sometimes. Arthur Eddington was the one that observed the eclipse that helped prove Einstein's theory, right? So in basically, I think it was 1920 that he did that, 1919 or 1920. Well, anyway, she went to a lecture by him, and reading her diaries, it's really interesting. She said she was thunderstruck by the lecture, and she said she could not sleep for 3 days after she saw the lecture. And so she decided to switch to astronomy. And she went to school at Cambridge and basically did everything that you could do, but she was not allowed to graduate because Cambridge did not grant advanced degrees to women. I think not until the 1960s. So she moved over to the US to go to Harvard Radcliffe, where she could get a PhD. And she developed a totally different stellar model, right, than the reigning one, right, about that it was just like Earth except warmed up. And it was not initially accepted by really anybody. And she actually had a caveat that it was probably spurious to get published. And it was like, it's kind of a neat idea, but it probably wasn't true. She did go on to teach at Harvard, by the way, and actually become department chair. It turns out her numbers were totally correct. And it's interesting because her dissertation on this is considered one of the most brilliant in stellar astrophysics of the 20th century. So you see, basically the sun's made up of, it's very much not like Earth. It's 92% hydrogen, and basically 92% by number. You can also look by mass. Let's look by mass. 73%, so almost 3/4 hydrogen, about 25% helium. So that makes up almost everything, right? That's like about 98.4%. All the rest are all these trace elements: carbon, neon, oxygen, neon, magnesium, silicon, so on, all the way up to iron. Astronomers call everything other than hydrogen and helium metals because what they care about is hydrogen and helium. So everything else is called metals. They're sort of like the things that kind of pollute stars. So you can see we have a whole bunch of mixes. What we get, what's actually going on inside the sun, of course, is nuclear fusion. But what a lot of people don't realize is this only happens in the very core of the star. That's the only place where temperatures are high enough and pressure is high enough to actually sustain that process. So really like the inner 10% of the sun. And a lot of this we know, and so, but we also know that the sun's very stable, which is good for us because it doesn't change in size, which means all the gravity pulling all this stuff together is being balanced by all the pressure from the fusion gas and radiation pressure pushing back on it. So there's kind of like a balance of forces on that. So that's really where all the fusion occurs in the sun, just inside. And in fact, it takes light anywhere from about 4,000 to 500,000 years to travel from the sun's core to the surface. Because what happens is the light gets generated, the energy gets generated, and there's so much pressure at the center of the sun that it doesn't go very far before it gets like maybe captured by an atom, then gets released, and basically interacts with all these atoms, and it sort of kind of bounces around for a while. Now, you see all kinds of numbers for this. Some people say it takes millions of years, but that's not. The more modern one really is more about 500,000 years. So basically, the light you're seeing today, like when you were outside today getting sunlight, that really basically was actually created with the fusion reaction that created it was about 500,000 years ago, on average. How the sun does this, of course, is nuclear fusion. kind of cool. Basically what it is, it basically uses 6 protons in. So basically that's 6 hydrogen. And basically what you get out is there's actually a whole bunch of cool physics that occurs. There's like some intermediate steps, and it's actually really cool if you like nuclear physics. And what you get out is 1 helium, 2 hydrogen, some neutrinos, and light. So you get a couple of gamma rays come out. There's a little bit of energy is released because when you actually weigh 1 helium and 2 hydrogen, it actually weighs less than 6 hydrogen. So that missing mass, missing mass is actually converted to energy. And that's the famous E equals mc squared, right? Energy equals mass times the speed of light squared, right? And when you do the calculations, it's just a little bit of energy that gets created, but there's an awful lot of helium awful lot of hydrogen being made into a bunch of helium in the sun at any given second. So it adds up to a whole lot of energy. And of course, that the missing mass there is what's actually converted to light. So when we kind of look at the sun, of course, it's got the core inside, and then there's different types of energy transport. There's like a radiation zone and a convection zone. But I really want to talk about the upper layers because that's what matters for us as astronomers. So the upper 3 layers are there's basically the photosphere, the chromosphere, and the corona. And so let's actually start with the photosphere. And this is really the surface of the sun. And you say, okay, how do you really get the surface? Because the sun doesn't have a surface you can stand on. The way astronomers determine it or classify it is where the gas gets optically thin. So as you get farther away from the sun's core, of course, there's the sun gets less and less dense. And so when it gets to a point where it's at a density where that we talked about these photons, bouncing back and interacting with particles, when there's a level when most of the particles escape, or the average the average particles escape. That's what we call the photosphere. So it's when it's become optically thin, and there's actually a formula for it. That's what they call the surface. And of course, that's what we really see. If you were to look at the sun, please don't look at the sun, without protection. But when you look at it, and when you see sunspots, that's actually where you see that you're actually looking at this photosphere. And so that's the density of the sun's low enough for most of the light to escape, right? The density at that point is actually less than the Earth's atmosphere, so it's actually pretty thin at that point. So, and this is actually where you see sunspots, and we'll talk a little bit about those. And this is also where you get the temperature of around 5,800 Kelvin. Inside of the core, it's closer to 15 million Kelvin. And so when you look at these sunspots, the sunspots are always cool to look at with a white light filter, though most of them are about the size of Earth, right? So they look really small, but they're actually the size of Earth. It's so basically you see all these transient sunspots. They were first discovered by Galileo in the early 1600s. I find that amazing because he looked at the sun with his inexpensive telescope, or his primitive telescope by our standards, but he was looking at the sun without any protection. So he did permanent damage to his eyes by trying to study the sun with a telescope. But it was important because he saw that the sun had spots in it. It was not perfect. That was actually a pretty big revelation at the time, because everything in the heavens was supposed to be perfect. And he said, no, it's got spots on it, Why do sunspots look black, and what are they? Well, it's because they were lower in temperature than the surrounding surface. So if you were able to pull a sunspot out and all of a sudden transport it to some other spot, it would actually look pretty bright because it's still pretty hot. But it's just compared to the surrounding sun, it's much cooler, which is why it looks dark. So when you actually look at these sunspots, you'll actually see they actually occur in pairs. And basically what they are, where they originate from, is there's these magnetic field lines in the sun. And basically it's sort of like a north and south pole of a magnet. It's really similar to, if you ever in physics class, remember they used to throw out iron filings around a bar magnet or something, or a horseshoe magnet, and you see them sort of line up with the magnetic field lines, it's exactly the same thing. So the magnetic field on the sun goes in one sunspot and out the other. In fact, it's magnetic field lines that are actually kind of holding the sunspots open, right? So just some examples. So whenever you see these sunspots, they occur in pairs. Sometimes one side of it may be hard to see, but they're always there. And you can see a lot of times material will shoot up, plasma will come up and follow those lines, follow those field lines. You can see it like in the two, both on the left and the right hand side. Material will come up and follow all those field lines. That's what these a lot of prominences really are. So it's I'm sorry, I'm having a little trouble with, for some reason, doesn't want to do that. So the way it kind of works is with the magnetic fields lines there, they're basically keeping the sunspots open. Because what that means is the material in the sunspots is cool. The reason it's black is cooled down. Ordinarily, that would sink down in with the convection of the sun. But the sunspots are sort of like if you put a shoelace through two holes, right? And you can't pull the material back down. So it's actually holding that material up, and it's much cooler than the surface. When you look at these sunspots, it's really interesting. They occur in about 11-year cycle. And there's like kind of a min-max sequence, and it's actually pretty reliable. You can kind of see in the bottom chart here that it's pretty reliable all the way across since we've been keeping track of it. And so this actually shows you about the last century. The actual physical number of sunspots, or the sunspot number, varies, but you can see that the highs and the lows are pretty reliable. And so a couple interesting things are, of course, that when you start near the minimum and you start getting sunspots, they're actually pretty high in latitude. And as you work toward the maximum, they start getting closer and closer to the equator. And then all of a sudden you'll see, basically all of a sudden it jumps back up. You get a maximum point really in the middle here. And then it gets, they start getting lesser and lesser as it gets near the equator. And then all of a sudden, boom, it jumps up again and starts to cycle again. One really interesting thing about it, sunspots, is they are very consistent, with the exception of there's like 50 years right here. It's called the Maunder minimum. And it's very interesting because it's 50 years, there were very, very few sunspots. And it was historically a very cold time in Europe because the sun is a little more active and puts out a little more energy when there's a lot of sunspots. We really don't know what happened here. They've been tracking sunspots really since Galileo first saw them, but there was this incredibly 50 years where it was just very, very where it was the sun was very inactive. And not really sure why. They thought maybe it was just an anomaly. Now some of the later research that's coming out indicates that it's possible that stars, that as they get near middle age, which our sun really is middle aged, about halfway through its life, it's possible there's a lot of magnetic changes in the sun, which could mean that our sun's starting to go through that transition to middle age, from a young star to an older star, which means that we might be the magnetic activity might get a lot more spotty on a cosmic time frame, maybe not in the next 5 years, but might get a lot more spotty, and then may even really calm down a lot, because we kind of see that a lot of stars kind of go through that early in their life. They seem to have a lot of magnetic fields, and then all of a sudden that seems to drop off, and nobody's sure exactly why. So it's a pretty active area of research, right? I will say this, even though I said sunspots can cause things to be brighter, and that it was historically a very cold time in Europe during the Maunder minimum, that I always put this again in for my classes, is it does contribute to variability. You can kind of see the cycle of total solar radiance, right? But you can also see that it is not driving climate change, right? And what's actually kind of interesting, or most interesting, is the sun's variability has actually been declining here over the last, 40 years or so. And it's actually one of these down cycles, but where temperature is rising. So I always kind of point out, you hear the argument a lot that solar irradiance is the driving force for global warming, and that's really not the fact. So I love this picture actually. This is a part of the solar cycle, and basically shows kind of number of sunspots. You can see this is a hydrogen alpha picture, so you see the sunspots are nice and bright. And so this goes from 1996 to 2006. You can see the sun's very, very quiet to really 2001 when it's really active, and then it starts dropping off again. So I think that's kind of a cool picture. Let's talk. Okay, when you look at a white light filter, I should bring this back to astronomy. When you look at the white light filter, you're looking at this photosphere. That's the layer you're looking at, right? So when you see sunspots and you talk to people about it, the next layer up is sort of like the sun's atmosphere, if you will. It's called the chromosphere. It's called the chromosphere because it has a distinct color. It's basically, you can see it during a full solar eclipse, or you can see it with an H alpha scope. And so when you look at with a H alpha or hydrogen alpha scope, that's where the chromosphere is active, is in that hydrogen alpha transition. So that's the 3 electrons going from the 3 energy level to 2. It emits very little light, so you really can't. The photosphere totally overwhelms it. But if you do, you can see it during a total solar eclipse. It always looks red, which is why all these H alpha scopes look red, right? Because it's that one line of emission from hydrogen. That's what goes on mostly in that layer. What is kind of interesting, and this is something that's still studied a lot too, is we talked about the temperature of the surface of the sun, the photosphere, and we can measure that, but the temperature in the chromosphere rises to about 35,000 Kelvin. So as the sun gets thinner, the temperature gets lower and lower, from 15 million to almost 1,500 degrees Kelvin. But then what happens is all of a sudden it starts increasing in temperature. And the exact connection between that, we think it has to do with the magnetic fields, but that's still very actively studied today to figure out the exact mechanism of the connection and why all of a sudden these outer layers get hotter and hotter. But it rises to this high temperature. It's very active in this hydrogen alpha line, and that's actually what you see. But it's really thin. It's like 10,000 times less dense than the photosphere, and that would be about 100 million times less dense than the Earth's atmosphere. So it's a very thin layer. But this is what you're looking at when you look at hydrogen alpha scopes. And this is the kind of thing you can see in hydrogen alpha. Of course, you can't see the Earth, right? I put the Earth to scale. But you see, when you look at the limb, you see these prominences. And I like this picture because it's got a couple different ones. It's got like that arc, this part right here sticking up. It's got a little arc right here. It's got kind of like this almost a fan shaped thing here. And there's names for a lot of these different types of prominences that you can see. And this is what you see with a hydrogen alpha scope. So you're looking at this layer above the photosphere. Right now, the sun's very active because it's near the peak of a solar cycle. So we see a lot of prominences. This one's actually huge. I'd love to see one this big. But there have been some really good ones here over the course of this year. We've done a couple of I've done a couple of events with a solar telescope, and we saw a couple of really big ones. So it's a good time to get out there if you have a solar telescope. Got a little video here. I'm not sure if everybody's getting audio or not, but that's okay. I just kind of like this because it gives you a good idea. One thing when you're watching this in H alpha scope, if you're out there if you're out there like doing a public event for 2 hours, these prominences will change a lot in 2 hours. So I mean, they actually have a pretty fast rate of change. And I think this is just this is from a satellite, but I still think it's a pretty good view. And you can see basically like the big arc right here. A lot more material following the arc. And you can just watch the changes. And it actually occurs quite quickly. And that's kind of neat when you're actually watching something that's changing, you know? I don't know why they put thunder in this video if you can hear it, because the sun doesn't really thunder. And if you look around it, you kind of see a little bit of the churning of the sun, the convection in the sun, of little different cells, because there's a lot of convection at the surface of the sun with material coming up, releasing energy and dropping back down. I think this is one of the best. I think it's really cool when it looks like this. Oh, let's see, it went the wrong way. So when you see these kind of prominences, if basically they burst, so like the magnetic field lines could snap. And when they do that, they release radiation. And this is what's a solar flare, right? So sometimes they can just snap, and there's really no prediction for when that's going to happen. And when they do, they release a lot of energy. Right? Like I said, the magnetism in the sun is not completely fully understood, but you do see this, and that's when you get these solar flares. Now, if it's big enough, it can actually do what's called a coronal mass ejection, and that reduces actual plasma. So, radiation is, just going to be like the electrons and some other and gamma rays and things like that. Whereas the coronal mass ejection is actually, basically protons and the hydrogen, basically the hydrogen atoms and electrons and all that kind of stuff. So you can actually get that. This is a picture from a satellite. One of the satellites, some of the solar satellites we have watching the sun now 24/7, they kind of have this blocking disk. This round thing is actually a blocking disk to block out the main light of the sun so that you can see what's going on inside the corona, the outer layers, and you can see things like these coronal mass ejection shooting off, right? You see the sun's actually very, very active at this point. So really that's kind of the difference, right? The solar flares are really energetic bursts of light and particles, right? And basically they're very powerful. When you see these things go off, they're like actually billions of hydrogen bombs. Um, and basically they move pretty fast, and they can they can get to Earth in less than 20 minutes. These CMEs are huge, are large clouds of solar plasma, and they basically go off, and they can actually travel quite fast. And if they're traveling fast, they're actually dangerous, because that's actually the ones that can actually cause problems with power grids and actually cause problems here on Earth. Probably the biggest one was the Carrington event. I think it was 1859. There was a very large one that traveled very fast. It was kind of a unique combination of circumstances that hit. So there's a lot of energy that hit at a very high speed, and basically it played havoc with the electronics. Fortunately, it was 1859. There weren't a lot of electronics. Mainly consisted of like telegraph offices basically catching on fire, from all the induced electricity from the magnetic field. So um, when you're looking at H alpha scope, you'll see a couple of different types of things. You'll see these prominences. Like I said, I can't promise that we'll see anything like this. Boy, that would be great, huh? A lot of them are going to be more like this or more like this down here. Uh, and those are what you call them when they're on the limb like this. When you look at them when they're kind of facing you, we call them filaments. There's really no difference other than they look different. And you see the filaments, see these dark lines here. These would all be these kind of prominences on the edge. It's just you're looking at them from above. So one thing that's interesting about the solar magnetic field, and one of the keys to why we go through the solar min and max, is it kind of gets all wound up. Initially, when you get to when you start, and they're very starting at the high latitudes, basically the sun's magnetic field is kind of all oriented, kind of nice and neat. But because of that differential rotation we talked about, it starts getting twisted up and twisted up and more twisted up. And then what happens is it eventually gets to the point where it gets so twisted up, it snaps and basically then just resorts itself into a nice smooth set of lines. And that's when it all of a sudden goes from everything being close to the equator, it snaps and goes back out and starts all over again. And in fact, what happens is the north and south poles of the sun actually switch at that point. So it switches every 11 years. But that's actually what goes on. And because of that differential rotation, that's why it gets more and more active as it gets near the solar maximum, right? So that's actually what's going on with regards to that. Finally, we get to, if you're looking at a total solar eclipse, you see the corona, the outer part. It's very low density, very thin. But the thing is, the temperature is somewhere around 2 million degrees. Or sorry, 2 million Kelvin. I keep using degrees. You're not supposed to do that with Kelvin. So again, the connection between that and the chromosphere and the photosphere is not fully understood. But it's very low density. It's not very bright. That's why you can only see it if you block out the main portion of the sun or if you get a solar eclipse. But if you get a total solar eclipse, it makes it really cool to see because you can see that nice corona, right? So something like this, and basically it's so thin and the sun's hold on it is kind of really ethereal. So a lot of this coronal gas will slowly escape as solar wind, right? And this basically pervades our solar system is solar wind. It runs about 500 kilometers per second, so it takes about 3 days to get to Earth, right? It's kind of interesting. The solar wind kind of carries along with it a lot of charged particles. And the good news for us is we have a magnetic field. We'd really hate it if we didn't, right? So our field, our magnetic field basically is pretty even and pretty well sorted, but it doesn't look this way in the picture. And the reason it doesn't is because the solar wind is strong enough. You see it kind of compresses this forward part. And then it kind of elongates this back part. So kind of what it looks like. A lot of particles flow up and around, but some particles actually get trapped. So what they can do is they get trapped in between these field lines in these blank spaces here. And they can get trapped in there, these energetic particles. These are actually what they call the Van Allen radiation belts. So for those of you that heard the term Van Allen radiation belts, that's what these are. And what happens is they lose energy. And then what they do is they can kind of fall in and follow these field lines and come in at the Earth's poles. And when they come at the Earth's poles, well, they basically interact with the atmosphere. And that's where you get the auroras. So basically, the aurora borealis or the aurora australis are basically that's what they are. Is these charged particles coming in and interfering or reacting with the atmosphere, right? So here's some cool pictures. I like this one the best. This is one from the International Space Station. When it kind of passed over. So it's kind of pretty cool to see it. And you can see the green is lower than the red. I think the red is oxygen and the red is nitrogen and the green is oxygen, if memory serves, but don't quote me if I made a mistake there. That's why sometimes you can see the red farther away. In fact, I think it was 2003 maybe, or 2007, when there was actually some very large solar flares, and you could see the aurora all the way down here in the Carolinas. And you could clearly see the red easy with the naked eye and make out details. The green was harder. You had to be in a little darker spot, right? So, but that's sort of my basic sun pitch. So let me stop sharing and go back to see if I put everybody to sleep or not. But does anybody have any questions? Chris, if you are talking, I believe you are muted, sir.
There we go. Talking to myself. Yeah, I've got a couple. You mentioned the rotation speed being different at different latitudes. Is it the same for Jupiter?
Oh, that's a good question. Actually, well, I don't know. I'd have to research it, to be honest with you.
Okay.
That's a great question.
Then also you mentioned surface temperature 35,000 Kelvin. I think it was in the
Well,
chromosphere. Yeah.
at the photosphere, it's like 5,800 Kelvin, but at the chromosphere, it jumps up to like 35,000
Okay.
Kelvin.
And then you also mentioned that the red that you could see there was hydrogen alpha. Is there any correlation between that? Because my understanding is that the higher the temperature, the bluer it gets, the colder the redder it gets. Is that correct?
Well, right. Yes. So that would be okay. Yeah, that's a great question because what you're talking about is like a black body curve is the energy that's put out by a black body curve, right? So if you were looking at any kind of solid object, what you would get is the temperature, the peak tells you the temperature. So as the temperature goes up, it gets bluer,
Yeah.
right? But the thing about this, the chromosphere is it's not a solid object. It's because it's such a thin layer, you can treat it like a gas.
Yeah.
And the only energy you're getting is from this one transition. Excuse me, the vast amount of energy you're getting rather is from this one transition, which occurs at a very specific wavelength, which is why it looks red. And in
Okay.
fact, most of these H alpha scopes, they usually have the band pass, the filter width.
Yeah.
It's usually like half an excuse me, is like half an angstrom or something. So it's actually a very narrow line to
Okay.
see that.
So I think what I'm trying to understand is that the temperature is 35,000 Kelvin. Is there any correlation between that and the hydrogen alpha wavelength, or are they just completely different things?
Well, yeah, it means that it means there's a um, it means basically that what's happening is the energy is about right, so that hydrogen the hydrogen atoms, the electrons are jumping from the 2 level to the 3,
Yeah.
the from the 2 orbital to the 3 orbital. And then what they do is they don't like to stay there too long, and they'll jump back down from 3 to 2
Yeah.
and release that energy. So yeah, there is a correlation at temperature. That's
Okay.
where it's very active right there.
Right. And that's where I guess I'm having a bit of difficulty understanding that red is usually lower than, say,
It is
2,000
if you were
Kelvin.
it were a solid object, that would
Yeah.
be true, right?
Okay.
I
Yeah,
think
the sun has a couple of things like that where it's like it kind of mixes several different things. But go ahead, Rob, was that a question?
well, what I was going to say is if you look at the whole spectra of the sun, there would be lines from probably the blue and green clear down to the red.
Right.
And the only one that's emitted at the chromosphere is the one at the red end. Doesn't necessarily have to do with the temperature, just because a lot of the spectrographs are black and white anyway. Uh, what it has to do is just that energy level that's transitioning right there, like Ian said.
Okay.
Right. There would literally be thousands of lines, absorption lines in the sun spectra. Yeah.
And the hydrogen's what, 3 or 4 main lines or something, and then they all. One
Yeah.
thing I always thought was neat about the sun was how it peaks in the green, and people always say yellow or white, but the black body peak was actually green. And I always use the example that the only organisms that can't move are plants, and so they reflect the main damaging wavelength that comes from the sun, and that's why plants are green. Biologists tell me I'm wrong, but it's actually the reflection of light for protection.
Yeah. So yeah, I'm not really an expert at that kind of thing. I'm not really sure. I'm not sure I've ever heard that before, but yeah.
Yeah, I forget where I heard that. Might have been It was probably some planetarium conference I went to.
But yeah, the sun's actually pretty interesting. There's a lot of really cool physics that goes on, not all of which is completely understood. It's really interesting when you can kind of dive into diving into the physics. It gets really interesting there because there's a lot of really cool things that go on between all those different layers and what's going on. There's a lot of statistical mechanics as well because there's so many atoms in the sun. You can use statistical techniques to figure out what's going on because not every atom's behaving exactly the same, right? But you sort of just want to get the large scale trends, right? The law of large numbers. So it's pretty cool. I guess I just kind of wanted to cover that so that, if people ever get questions on the sun, like when you're out doing solar observing with either an H alpha or a white light filter, you can kind of talk a little bit about that. Anybody have any more questions that hopefully I could answer?
You mentioned aurora when you're going through that, and I'd always wanted to see them. And when we actually immigrated to the States, it was a really cheap flight via Iceland. And we did it because they gave you business class. And it wasn't because it was business class, it was we got more luggage to emigrate with. We flew to Reykjavik and then flew from Reykjavik to Cleveland. And on the second leg, we got to see the aurora from the aircraft. And they turned all the lights off in the aircraft, so we could say it was really cool.
Oh, I bet that was really cool.
Yeah.
Yeah, it's always kind of hit or miss when you go to these trips to see it, right? Yeah, I saw it, like I said, from the Carolinas. That one time it was really active. It was pretty amazing because I had a friend who called me and said, "Go outside right now." And I said, "Well," he said, "Go outside right now on your deck. Just stop talking to me." He said, "Stop talking, go out." And I went out and it was just shimmering in the sky. It was really incredible.
Yeah.
So
Yeah,
I would love. Sorry.
That was one of my earliest memories in astronomy. I was a little kid, and I think we were in southern Pennsylvania, and my parents woke me up in what seemed like the middle of the night, but it was probably only like 9:30 or 10, and because the aurora was visible.
It's well worth it. I hope we get another good one down here. So that would really be great. Or maybe I'll get to go and see one sometime. I always looked every time I was in Canada, but I never hit it just right. So. All right. Does anybody have anything else you want to add before we turn off the live stream?